Look up. Past the rustling trees and streetlights. Through the clouds and contrails left behind by roaring plains. Into the night sky. And beyond that, wonder. Since time immemorial, we've reached out to the planets and stars for navigational direction and meaning. And today, planetary astronomers continue to look to the stars to find a final answer to that question. What is out there? I'm Jerry Broughton, a map historian, and welcome to What's Your Map, an Oculi Mundi exploration. In Season 2, we continue to speak to people who live, love, and work with maps, making, preserving, interpreting, and being inspired by them. In each episode, we ask our guests to unfold a map that is special to them and to tell us the story that lies behind it. To follow the map as we talk about it on this podcast, go to oculi-mundi.com. For thousands of years, humans have gazed up at the stars and wondered if there is other life out there. Today we have someone who has helped bring us one step closer to finding out. Dr. Heidi B. Hammel is a planetary astronomer with NASA's James Webb Telescope project, where she investigates the potential for life in planetary systems, including our own. Dr. Hammel is also the Vice President of Science at AURA, the Association of Universities for Research in Astronomy, a non-profit that manages some of the biggest telescopes in the world and in space, like the Hubble Space Telescope. For the better part of 30 years, she studied the ice giants, the planets Neptune and Uranus. Heidi, welcome to What's Your Map? And please tell me, what map have you brought us today?
What I've brought to you today is one map from a book of maps called the Norton Star Atlas. And it's an atlas of the heavens, just one segment of the sky that shows you stars and constellations. This particular map is an example of the kind of tool that I used to become an astronomer, to learn how to study the sky, laid out in a way that an average person could look at the sky and then look at the map and figure out their way through the heavens.
It's interesting, isn't it? Because mapping really, we think, is very much about Earth and terrestrial life. But actually, we go right back, and some of the first great classical map making is of the stars, which is of maps like this. And it's a sort of oval-shaped map, which has Roman numerals across the top. And then this amazing green, it looks like algae that runs across from the middle left to the right. And then with the constellations, walk me through what I'm looking at, because I'm sort of fascinated, but also a bit lost here.
Sure. On the Earth, we take our circular Earth and we break it up into segments that we call latitude and longitude. So anyone who's worked with a map understands, the latitude goes from the north to the south through the equator. Longitude goes around the Earth. Well, if you imagine projecting that latitude and longitude grid up into the sky, you can have a same kind of a grid system. And so in this map, you're looking across the top. The Roman numerals correspond to what we call the right ascension, which is the equivalent of longitude on an Earth map. And then there are lines across the map, horizontally, that correspond to what we call latitude on Earth, but up in the sky, we call that declination. So it's the same concepts of latitude and longitude, but they just have astronomical terms.
So this is a bit like looking at a terrestrial globe, but we're looking up rather than thinking about the Earth. So it looks like segments of an orange, aren't they, Heidi?
Exactly.
It's like peeling back an orange. So this is what we call, for a terrestrial globe, this would be a globe gore in this shape. But you're explaining that this is, as it were, a segment of the night sky looking up.
That's exactly right. I didn't know the technical term. I was thinking orange is peeling the orange myself. But now I know the word gore. I'm not a cartographer. Exactly. Exactly. This is a gore or a slice of the night sky. I picked this particular one because it has some constellations or collections of stars that many of us are familiar with, specifically the constellation Orion.
Where is that?
It's below the green stripe, off to the side on the left. There are some bright stars, and you can see the belt of Orion and the shoulders and the knees.
Yes. And Taurus is to the right,
exactly.
sort of almost in the center. And
That's
Aries
right.
is up in the right.
Yeah. Taurus is a very recognizable pattern in a V shape of stars. That's useful for an astronomer because you can look in the sky and there's bright stars and then there's not bright ones. And you look back at this map and you can immediately pick out the bright stars. So it helps you navigate yourself in the sky quite easily. Oh, you were asking what that green thing was. That green thing corresponds to our Milky Way. And so if you looked up in the sky, that part of the sky in a very dark sight would be kind of a lighter milky colored. It's actually made of thousands and millions of stars that are really too faint for us to make them out individually, but they combine to make what looks like a white cloud, which the ancient people called galaxia, right? Looked like milk was spilled, and that's why we call it in English the Milky Way.
And so much of what you're describing here is from the classical Greco-Roman tradition. So you have the Latinate terms, you have the Latinate use of numbers, Andromeda. This goes right back to a Greco-Roman astronomical tradition, doesn't it?
Yes, and it also goes back to the astronomers in the Middle East. There are many stars here that have names that come from languages that are not of the Greco-Roman tradition. For example, that brightest star in Taurus is Aldebaran. And that Al is, that's part of like algebra. There are many other Altair. Many of the stars have those different roots in them. They're not just Roman and Greek.
I'm so pleased that you said that. I mean, it's something that I'm fascinated by in terms of the great father of map making is Claudius Ptolemy, who comes from Egypt. And he's seen as a sort of Roman Hellenic traditional scholar. But of course, his heritage goes east and west. And I love the fact, look at this, because the first thing that he does, he writes this book called The Geography in 150 AD, where he says how you map the Earth. But he's also an astronomer. So it's sort of right there at the heart of really your discipline, isn't it? The way in which you map the stars, but it's also got a mixed scientific heritage that's not just Greek and Roman, it's also Arabic as well, because it's fused, it's mixed in that way, because everybody's been mapping the stars forever.
Absolutely. I mean, that's a human thing to do. And whether it is in the Arabic tradition, the Roman tradition, or the Middle America, Mesoamerican, Aztecs, Mayans, they all looked at the skies. They all mapped the skies in their own way. That was people's way of navigating on Earth. So it's a human thing, I think, to be mapping the skies.
And just give me a sense of some of these other issues on the map, because you've got these stippled areas down towards the bottom, and I'm trying to work out what's being defined there. Down in Lepus, you see in Columba down in the bottom left-hand corner, these little dotted lines. What do they represent? When
we look at the sky, it's like a big thing, right? So we try to break it up into real estate, if you will. And so these dotted lines are outlining regions of the sky that we call a constellation. And so, for example, the constellation Lepus, which is the hare, I don't see a rabbit there, but someone did in the past. And there's a box around it, and that all the stars inside that box are considered part of that constellation. It's the equivalent of country boundaries on the surface of the Earth. These constellations are how astronomers communicate to one another where to look in the sky. And so, if someone said to me, I'm looking at Alpheus Canis Majoris, which if you look to the far left of this Norton map, you'll see Canis Mag, M-A-G. That's the big dog. And the primary star there is Alpha Majoris. That's the brightest star in that constellation. So if you said, I'm looking at Alpha Canis Majoris, I would know which part of the sky, that area called Canis Majoris, and I would look for the brightest star in that sky.
Just explain to me something. So in the summer, I was sailing on a boat in Turkey, and the skies were amazing, and I slept on deck one night, and I looked up at the stars, and I was trying to sort of orientate yourself. How do I use this map to do that? Because I also think, okay, I'm here in the Mediterranean and I'm looking up and I'm on a planet that's moving. And what I see when I look up is different for what somebody might see if they're in Australia looking at the night sky. How do you orientate yourself on Earth in relation to these maps of the universe?
What a good question. We have maps like the one I'm showing here that cover the entire sky. And we know which parts of the sky are visible at different times of the year. And we also know from your particular latitude and longitude on the Earth, what part of the sky is above you on a specific day of the year. And so if you were in Turkey and it was the summertime, you would not see Orion. Orion is a winter constellation for us.
Right.
So you would have to flip the pages of the book. You would have to say, oh, okay, it's date X, whatever the date is. And then you would have to know this is part of what being an astronomer was, not only modern times, but in ancient times, which of these maps you would need to turn to. And so you would say, oh, this date, that means I'm looking at this particular right ascension or longitude, and I'm at this latitude on the Earth. So that means above me would be this declination. And that would tell you what map to pull out, what page to turn to in your atlas. So you would have to do a little bit of math.
I think that's what's so amazing to look at this map that so presumably fascinated you. I really want to know the story of why this map so engaged you, because, this map is over 100 years old. What were you doing when you first saw this map? I really want to know, because this must have so beguiled you, excited you, amazed you. Tell me about what happened when you first saw this map, Heidi.
Well, prior to seeing this particular map from the Norton Star Atlas, I was mostly a kid who was just looking at the sky, and I started to recognize patterns in the sky. Living in North America, the Big Dipper is a very easy star pattern to see. Orion, which I showed you, I gave you the map with Orion in it, a very easy pattern to see. So I kind of had a sense that there were patterns in the sky. It wasn't until I started taking an astronomy course in college where I encountered this map. And it's like, now I'm starting to understand, like, there's a whole map. These patterns, they're easy to recognize, but they're more than that. They are a guidepost in helping us understand what is out there and where it is.
How quick has the science changed? Because we're not relying on books like Norton's Star Atlas anymore. And I'm fascinated that you are, if I may say, you're clearly somebody who's really at the cutting edge of how we're understanding the universe. And yet you come in with this beautiful, but it would seem to me in some ways very outdated way of looking at the stars. So just fill me in on that in terms of your own development, in terms of working in this field, and how rapidly the science has changed, and I guess particularly as we've gone computerized and into digital technology, which is now driving so much of the work that you're doing.
You're absolutely right that the technology has changed tremendously just in the course of my professional career. I did use this atlas when I was starting to learn. And I was part of this early generation that we actually started to have telescopes that had computers that could, you could tell it where to look in the sky. You didn't have to physically move it yourself. We had things on our telescopes called setting circles, big, giant brass wheels that had the numbers of the right ascension and the declination. And you would physically have to move the telescope to line up with the things that you pulled out of the atlas, like Norton's. And that's how you would point the telescope. That isn't how we do it anymore. Now everything is computerized. But it was a stepwise process. Initially, even 20 years ago, we had things called almanacs that were published every year by...
What? You used almanacs 20 years ago? This is wild.
Yeah. I think the reason I picked an older map like this, I think it's important that even astronomers who are working today be grounded in understanding where in the sky they are looking. Like, when you're using a telescope like the Hubble Space Telescope or James Webb Space Telescope, you're basically just interacting with your computer terminal. You write a proposal on your terminal, and if it's evaluated and if they decide that it's good science and they're going to do it, part of that proposal is you're telling them where to look and when and what colors you want to look at. And it all just sort of happens by really, really smart engineers and scientists at the Space Telescope Science Institute. They radio the information to the telescope up where it is up in the sky. It takes data, it radios back down to Earth, and you get an email saying, your data are now in the archive. You may access them.
Before we continue, I just wanted to say that I'm so pleased you're able to join me on my journey into the world of maps, their stories, and the people who love them. If you're enjoying our podcast and don't want to miss a future episode, then please do consider subscribing and leaving a review when you finish listening. And if you think your friends and family might be missing out, why not ask them to give us a listen too? Back to the rest of the episode. As somebody who works in the earlier classical, medieval, Renaissance period, we know that most people who are mapping anywhere, be it the Earth or the universe, they don't call themselves map makers until actually relatively recently. They call themselves cosmographers. So in the Renaissance, people would still say that they were cosmographers. They were mapping the world in relation to the heavens. We're going to talk a bit about that with you because, in a sense, to be talking about tracking and understanding life on this planet in relation to the universe is not dissimilar, really. You're still doing something in that cosmographical tradition. I mean, do you have a sense of that you are dealing with that long human history of mapping the stars, but in relationship to our tiny little planet here?
Absolutely. I think in your introduction, you talked about the work I do with the James Webb Space Telescope and the program's specific science aspect that I work on with that telescope is planetary systems and the origins of life. And we're using this incredibly sophisticated space telescope to be looking out into our solar system, the planets that surround our star, Sol, and try to learn about what they're made of and whether there's the potential for life there. And yet we're also using this telescope to look at other planets around other stars. Something that's not captured here in the Norton Star Atlas is that every one of these stars, we think, has a system of planets surrounding it. You can't tell that by just looking at a star atlas, but we've used increasingly sophisticated telescopes over the past 2 decades, and every planet that we are able to probe with enough clarity and sensitivity, we find it seems to have a planetary system around it. So if you want to take it kind of a step further, when you look at Norton's Star Atlas, you're also looking at an atlas of where planets can be found in the cosmos. And on those planets, we are working to try to understand what is there. And by looking at how that planet's atmosphere absorbs certain colors of the starlight, we can actually make out what the composition of the atmosphere of that planet is.
I want to take you back to 1994 because you led the team that investigated Jupiter's this visible wavelength response to the impact of a comet, Shoemaker-Levy 9. You were leading and analysing the photos of that event, and obviously this is an attempt to understand a sort of dinosaur extinction moment if it hits the Earth. Give me a sense of the sort of tech and the science involved in that moment and what you were doing there, because it seems almost a bit sci-fi, but it's not really, is it? Because these are really serious issues that the tech and the science is engaging with. And you were there on the ground, as it were, in 94. Tell me about that.
Yeah, so let's start right away with how that comet was found. It was found by people taking pictures of the sky and making maps of what they see. And they were trying to get some pictures near Jupiter, and they found this odd object that seemed to move in these maps that they'd taken of the sky near Jupiter. And that was discovered to be a comet. And the team at the Jet Propulsion Laboratory in Pasadena discovered that this comet was in orbit around Jupiter, and that they could predict its orbit so well that they knew that several months later, this comet would actually hit Jupiter. And so every telescope on Earth made plans to watch it, because this was the first ever prediction of an interplanetary impact. We didn't know what we would see. I actually was of the camp that we probably wouldn't see anything, because Jupiter's a huge planet. Comets are balls of ice, and this was a big ball of ice, like a mile across. That's big. But hitting a planet like Jupiter, I was not convinced. I made this really big, complicated, like 6-foot-long chart that was the whole week of the impact. It was a week-long event because the comet was actually shattered into 24 pieces. And the pieces were coming in sort of like a train. It was like a train, and the first car would hit, and then the next car would hit, and the next car would hit. And so we created this whole map, and we developed our observational sequence for the space telescope to use, and all of that is loaded up to the telescope, and then we just sat there waiting. And
I'm looking at the image. I mean, Heidi, it's kind of extraordinary. So it's Jupiter imaged by Hubble in 94, and it shows the impact site, and then the same impact site mapped to the scale on Earth, and it shows, well, all of North America, most of the Atlantic would be immediately obliterated. I mean, it's shocking.
That's what we call a biosphere-changing event.
Is it now? It's just the end of life.
Well, pretty much, I mean, if you're not under the impact itself will create huge heat pulse that would start fires everywhere. And those fires would fill the Earth atmosphere with smoke. And in fact, when we talk about the biosphere changing event that probably killed off the dinosaurs, we suspect it might have been a giant impact that took place off the coast of Mexico. Chicxulub is the location. The dinosaurs weren't all congregated at that place at the Yucatan Peninsula in Mexico. Dinosaurs were like all over the earth, right? So why did
They're all on holiday in the Yucatan.
Yeah, I guess so, right? There's a convention happening at that time. No, they're everywhere. So it wasn't necessarily the impact itself that killed the dinosaurs. It was the impact's effect on the Earth, the fires that started, the fires that made huge smoke plumes that then circulated around the Earth. And those smoke plumes block out the sunlight. Vegetation dies. All the little mammals that eat the vegetation die. The dinosaurs have no mammals to eat. So it's a sort of a concatenation of terrifying events that take place after the impact, and not only the impact itself. I just want to know, have you yourself ever seen a shooting star?
Yes, in Turkey in the summer when I was on deck. Yeah, we watched.
You have witnessed an interplanetary impact. That's what that was. A shooting star is like a piece of rock or an ice ball that hits the Earth's atmosphere and burns up as it comes in. And that's what leaves the shooting star trail. So impacts happen all the time. We worry about the big ones. So what do we do if there is one? Well, the first thing we'd want to do is move it out of the way so it doesn't hit the Earth. And that was the point of the Double Asteroid Redirect Test, the DART mission. And what essentially happened is NASA took a spacecraft and it smashed it into the moon of an asteroid. And so when you whack the moon with the spacecraft, you could push it out of orbit. That was the hope. And then they measured the change of its rotation period around the main asteroid, and they changed it. They moved it.
It did.
Yes. So that is good news. We now know that if we can, whack it with something big enough, we can push it off course so it won't hit the Earth.
I mean, this is real Hollywood stuff, isn't it? And I have to ask you this. You must be modeling the probability that will happen. You must be. I mean,
of course. Yeah. Yeah.
Well, you've come on this podcast and you seem quite upbeat.
Well, the way I do. I am upbeat. I give talks about cosmic collisions. I give a whole talk about this. And at the end, I'm like, okay, so let's stop. Like, what are you really scared of? And what should you be scared of? What do people actually die from? And like, number one, car crashes. Like, did you drive here to hear my talk today? That's far more risky than the risk of being killed from an asteroid, right? Now, it's true that if a giant asteroid hit, it would kill possibly lots of people. And so we have to measure risk differently, but they're rare and people overblow it. People are really bad at estimating risk.
Yeah, but having said that, Heidi, you are quoted as saying that part of your job is about, quote, protecting our species from the universe, which I think is a lovely phrase. Unpack that.
We are building very large survey telescopes right now, like the Vera Rubin telescope in Chile, like the Roman Space Telescope. And these telescopes, of course, will be studying the universe and cosmology and supernovae and nebulae and all that great stuff. But they will also be creating a census of all of the potentially hazardous objects that could hit the Earth. And by creating this census, we are effectively buying planetary life insurance. We will be able to figure out where all the hazardous objects are and hopefully find them soon enough that we will be able to deflect them so that we don't encounter a species-ending event like the dinosaurs did. One of the jokes we have in our community is like, the dinosaurs died because they didn't have a space program. They weren't watching the skies. They weren't predicting what was out there. They did not have a deep understanding of the celestial map, so far as we know. But we, humanity, we can do that. And, I am, in my small way, part of this team that both creates the tools and the technology so that we can understand what the potential hazards are out there. And I am also out there trying to help communicate the fact that it's important what we do, because it's not a question of if Earth will ever be hit by a big asteroid. It's simply a question of when and whether or not we can do anything about it before it happens.
It's interesting, isn't it? Because, of course, everybody's going to want to ask you, your job is to study planetary systems and the origins of life. So, do you believe that there's life out there, etc.? But what's interesting is, from what you've been talking about, you're as much interested about the maintenance of the origins of life here as any other forms of life out there. Is that a fair description of what you think you're doing?
I think that is a fair description. We only know of one planet that has life on it, and that is this precious planet that we live on today. I think it's incredibly important for us, humanity, to care for this planet, to try to understand this planet. And one way that we can do that is by making sure that we study other planets as well. Because we only have our one planet here, and it's had one evolutionary track to get where we are today. How is our planet going to evolve in the future? One reason I get very excited about studying planets in our solar system, worlds in our solar system, even the moons, and planets around other stars, is they give us a much more robust understanding of what makes planets work. I think that understanding our Earth and our atmosphere and our oceans and our lithosphere, like the rocks, and our interior, we understand that better when we have not just our one example, but the now thousands of examples of planets we know of around other stars, and understand how they tick, how they work.
What is it that's really exciting you? Can you point me to something that you say, this is going to really be an exciting innovation that the tech is going to change our perception of completely?
I'm going to give you two things. One of them is our ability to study the atmospheres of planets around other stars. We're working now on a telescope called the Habitable Worlds Observatory, and it is specifically being designed to see if we can find evidence for the potential for life on an Earth-like planet around a sun-like star. If we find evidence, that's a game changer, scientifically and philosophically. The other thing is the universe is not just expanding. The data show that as it expands, that expansion gets faster and faster. We call it dark energy. The dark just means that we don't know.
We don't know.
We don't know. We don't know what it is. And there's all kinds of like mathematical terms I'm not going to go into here that people describe. It could be this or that or the other. But the bottom line is we don't know what is doing that. And so some of these new telescopes with the vast quantities of data that are coming down, they're going to use a couple of different ways of trying to probe the universe to see if we can figure out what this actually is. If we figure that out, there's going to be a lot of buzz. There's going to be a lot of Nobel Prizes.
There will be. When you do, can you come back onto the podcast first and tell me? That would be really, really handy if you do that. I mean, the infinite expansion of the universe and also this kind of conversation. Heidi, it's been an absolute pleasure. It really has. We could carry on talking forever and ever and ever. Dr. Heidi B. Hammel, thank you so much for joining me on What's Your Map?
Thank you. It was a delightful conversation.
Thank you so much for listening. I'm Jerry Broughton. This has been an Oculi Mundi exploration. The producer is Jill Achineku, and it's a Whistledown production. Oculi Mundi is the online home of the Sunderland collection of antique maps and atlases. You can read more about the Sunderland collection and send us suggestions for future maps to explore at oculi-mundi.com. That's oculi-mundi.com. Why not continue your journey with me by subscribing to this podcast? That way you'll never miss an episode.